Today I want to talk to you about tensors. So tensors arise in different places, and for our concerns, if you remember the Euler equations, we ended up dealing with the momentum advection tensor, this rho uu over here. And before I get to that, actually I want to use the stress tensor, tau, as an explanation, to give you an intuitive explanation of tensors, and then we'll get back to this guy over here. We haven't dealt with the stress tensor yet because right now we're dealing with inviscid flows, but we will get to it. Now, if you take a solid, and this is the kind of idea behind the stress tensor, if you take a solid and slice it at some point over here and you pick a point, then depending on the slice, you're going to have an internal force that looks like this, for example. Now, if you slice it in another direction, another way, again, at the same point, the force vector may point in a different direction, have a different magnitude. So in principle, depending on the orientation of the slice, you have an infinite number of orientations and magnitudes for these forces. However, there is, you can show from continuum mechanics that to describe the complete state of stress or the forces in a solid, stress is just force per unit area, all you need is to get the forces on three mutually perpendicular planes. And that's why we typically draw our fancy control volume like this. Okay, it's kind of control volume cube over here, and okay. Now I'm gonna take this orientation over here, x, y, and z. And it turns out that to describe the state of stress at any point here, all you need is the stress vector on three mutually perpendicular planes. So essentially over here, let's say you have a vector kind of pointing in that direction. Let's call this guy A, vector A. And over here you have vector B, and over here you have vector C. Okay, so if you know A, B, and C, that's enough to describe the entire state of stress in this solid. Now, A, each one of those vectors, actually has three components aligned with the three basis vectors for the x, y, z coordinate system. So we're going to call this one A1, and this one A2, and this one A3. And same thing for B. We're going to have B1, and we will have B2, and we will have B3. Same thing for C. We're going to have C1, C2, and C3. So in other words, A is simply A1I plus A2J plus A3K, and B is B1I plus B2J plus B3K, and C is C1I plus C2J plus C3K. Okay, so in total, we actually have 9 components to describe the state of stress at a point. Now the question is there a smart way to put these together, to index these together, so that we don't have to refer separately to A, B, and C, and then their individual components? Turns out that yes, but we need an additional number that allows us to tell where we are on the cube. So if you think about it, this A vector happens to be on this face, and the B vector is on that face, and the C vector is on the Z face. So we're gonna, what if we use the face as this additional index? Okay, so if we call this guy the X face, because it is perpendicular to the x-axis, right? The x-axis is pointing in this direction, and we call this guy the y face. Okay, we call that guy the z face. Then, what if we use the face, okay, as an additional index to allow us to describe where we are? So, in other words, when we refer to A, to the components of A or to A itself, we can use the z face in addition to the index of the individual components of A to say, oh, we are on the x face, and these are the components on the x face. We are on the y face. These are the components on the y face, etc. So we introduce the notation tau I j, where, okay, so let me write this one here, tau I j, where I refers to the face and j refers to the direction. Okay? And so if we are on an x face in the x direction, so let's say on a x face in the x direction, tau xx, that gives us which component? It gives us a1. Okay? What about, and that's, you can also index this as tau 1, 1. Okay? What about tau xy? So that's the component on the x face in the y direction. That will be a2. And tau zx, that is, tau xz, that is on an x face in the z direction. So that gives us a3. Same thing here. Tau yx is on a y face in the x direction. So that gives us b1. So that's y face, x direction. Tau yy, that's the component on a y face in the y direction, b2. And tau yz, that's the component on a y face in the z direction, that gives us b3. Finally, tau zx is the component on a z face, okay, in the x direction, so that's c1. Tau zy, component on a z face in the y direction, that will give us c2. And tau zz on a z face in the z direction, that gives us c3. Now, the forces that act, if you think of this as a fluid control volume, you know, in the x component of momentum, it's only those components acting in the x direction that matter. So A1, B1, and C1. So we're going to be dealing with this guy for the x momentum component. X momentum component. And same thing for y momentum, same thing for these, for z momentum. So it's just really a bookkeeping, a way to do some bookkeeping. Now, if you think of a vector, u as ui plus vj plus wk, we only needed the three basis vectors I, j, k to describe the vector u. That was enough. For the tensor tau ij, we need the three basis vectors I, j, k paired in twos. So you get the 1, 1 direction, 2, 1, 3, 1, 1, 2, 2, 2, 3, 2, etc. So that's why you have 9 components. So that's 3 to the power 2, that's equal to 9 total components. Another way to think of this is that you can write this entire tensor using the pairs ij by just stacking them next to each other. So for example, tau 1, 1, which is tau xx, that's equal to a1 I. So that's on a I face in the I direction, okay? Tau 3, 1, for example, that's on a, so that's tau zx, that's on a z face in the x direction. So that will give us z face in the x direction, that gives us c1. in the on the z face in the I direction. Just put the vectors next to each other, ij, etc. So therefore, tau ij is written as a1 ii plus a2, what is this? I face, j direction, ij, plus a3 ik, plus b1, that's on a y face in the I direction, plus b2 y face y direction, plus b3 y face z direction, plus c1 z face I direction, that's ki, plus c2 z face y direction, plus c3 z face z direction. That's how you express a tensor. Just like we write a vector as ui, vj, wk, we just pair the three basis vectors, write them in pairs, and that gives us the 9 components of a tensor, specifically here the stress tensor. Next, we are going to talk about the rho u tensor, or u rho u if you want. Now, a neat way to write this, to expand this or get the components of the tensor, we said you could use the matrix vector notation that I showed you earlier, but there's an even easier way, is to just say this is rho ui plus rho vj plus rho wk, just multiply it by ui plus vj plus wk. All right, so that's what this is, and then you just simply multiply these, so you get rho u I, and we'll explain what these are in a second, plus rho u v ij plus rho u w I k plus rho v u j I plus rho v j j plus rho v w j k plus rho w u k I plus rho w v k j plus rho w w k k. Okay, so what does this thing describe? It describes the transport of momentum with the velocity field. So for the x component of momentum, x component, rho u, this guy is simply rho u u, and that's equal to rho u ui plus rho u vj plus rho u wk. So u, v, and w, these velocity components, are transporting the momentum rho u, the x component of momentum, through the different directions, right? So in this case, the second index is really not a face like with the stress tensor. It's the other component of, it's a component of the velocity field, or the other components of momentum. Okay, same thing. Y momentum rho v is also being transported by the velocity field, so that gives you rho v u, or rho v ui plus rho v vj plus rho v w k. Now the two indices here, that's what they're telling you. The first index over here tells you which component of momentum you're transporting. The second index tells you what component is transporting it. So II is transporting the x component of momentum using the x velocity. Ij is transporting the x component of momentum using the j velocity, and rho and ik is transporting the x component of momentum using the k velocity. Now, we take the divergence of this guy to get us the net advective components. But the ordering here is a little bit skewed because from ahead of time, I can tell you that these are the three components that will contribute to the x momentum equation. But the ordering of these guys is a little bit off, yet the tensor will give us the correct components. So the interpretation is still that this is rho u being advected by v and rho u being advected by w, although the order is just a little bit off. So this is how we would take the divergence. Div rho u u, we simply just spill this out, just like we did here. We write d by dxi plus d by dyj plus d by dzk dotted with this whole thing over here. Okay. Now, you just apply the operator to each term. So, for example, we start d by dx and we dot it with the 9 components. So we get d by dx of all of these components. So we have an I dot d by dx of all of these components, rho u I. Now be careful, you have to put these guys inside the derivative. In this case, they can come out because they don't change with x. However, for cylindrical, spherical coordinates, the unit vectors can change with direction, so you have to be careful. So just so happens in this case that this is what we get. We get I dot d by dx of rho u. So so I dot I is 1, and you get d by dx for rho u I. Okay. Now, same thing here. So we get the first component d by dx I dot I is 1. So that gives us plus d by dx of rho u v j. Right, so left with j, and same thing, I dot I is 1 plus d by dx of rho u w. So again, d by dx of this guy, I dot I is 1. We get the kth component. And then the rest of them are all 0 because I dot j, I dot j, I dot j, I dot k, I dot k, I dot k are 0 plus. Now d by dy, now we have a j dotting this, so j dot I will be 0. So we get d and j dot j is 1, so we only get this non-zero, this row as being non-zero. So we get d by dy of rho v u, j dot j is 1, so we get an I over here, plus d by dy of rho v v j. So we get j dot j, j dot j, and plus d by dy rho v w k. The rest are 0. And finally, d by dz, we have a k dot I 0, dot j, dot j, dot j. They're all 0 except for the last row. So we get d by dz rho w u, k dot k is 1. We get the I component plus d by dz of rho w v j plus d by dz rho w w k. Now, these guys will contribute to the x momentum component, x momentum equation. And these guys will contribute to the y momentum equation, and these guys will contribute to the z momentum equation. Now, the ordering here doesn't matter. You could express this as u, rho u. It will change the indices here, but the result, these guys will be the same, because the way I like to interpret this is because this is the I component, corresponds to the I component, x component of momentum. We're transporting rho u being transported with the velocity u v w. This ordering will retain rho u, rho u v, and rho u w, but they're all the same, so there's not going to be a difference. Now, one last thing to consider is the weak form. So remember that div rho u is equal to rho to rho u dot grad u plus u div rho u. And then we combine this with the continuity equation divided by the density, and this term just simply gave us u dot grad u. I want to point something out, that this expression, the way you evaluate this expression is you have to evaluate this one first, u dot grad applied on u. And u dot grad is really easy to evaluate because that's just an operator. Vector dot vector is going to give you a scalar operator. So u dot grad is simply ui plus vj plus wk dotted with d by dxi plus d by dyj plus d by dzk, and that's equal ud by dx plus vd by dy plus wd by dz. Then applied on the velocity vector field, you just simply d by dx of u plus vd by dy of u plus wd by dz of u. Now be very careful when applying this in cylindrical coordinates because you have to take the derivatives of the unit vectors. Things are you get a few extra terms when you're differentiating the unit normals in cylindrical coordinates with respect to the r and theta directions.